Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akari Wisharuddin. So, my group members is Muhammad Farhan, Muhammad Zulfitri, and Amirul Shahmi. So today we want to present about the design of and analysis of the feedback speed control system under uncertainty of in maintained load variation in EMK31103 in a subject control system. So for introduction, we have the speed regulation in critical industrial draft system. The load torque variation introduce speed of disturbance. Open loop system are enable to compensate disturbance. And lastly, feedback control is required for accuracy and robustness. So next is about the problem statement and objective. So we have the maintain constant motor speed under a certain load condition. So design is a stable feedback control system. Minimize steady state error and overshoot. And lastly, for ensure robust performance against disturbance. So as you can see is in this slide we have the P control design. We use the P control design and PI controllers design. So we go first for the P controller design. We have UT equal to KP ET. So this advantage is for simplicity, very easy implement and tune only one parameter. So the speed reduced in rise time in making the motor reach in the target speed faster. So in this controller we have the limitation. So we have the steady state error ESS. It cannot be eliminate the error entirely to speed control as the speed near the set point. So the DC motor we have the lack of enough push to overcome friction or load lah. And the instability very high against can cause the system to overshoot or oscillate lah. So next we have the PI controller design. So we have the formula and chosen gains of KPKI. So that KP is around 2 to 5 for initial response. And next KI we have 5 to 20 to wash out the steady state error. And of course we have the advantage of this controller such as zero state error. The integrator continues to increase the voltage until the error is exactly zeros. This is crucial for maintaining pressures. And secondly is a disturbance rejection. It is too much pattern in returning the set point when the sudden load uncertainty in applied to the motor. So we have the limitation in the controller. First is overshoot. The integral action can cause the speed of the overfly the target before settling, and sluggish recover if not tuned correctly. So that can be to lead the slow of the settling time and integral wind up where the motor stay at the maximum voltage. This is too long. Thank you.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Arifan. So I will explain about the closed loop performance for P controller. So this graph show the closed loop response of the system using a P controller. So the output increases smoothly over time at the controller, reduces the error between the set point and the system output. So the response is stable with no overshoot or oscillation, indicating that the proportional gain is well tuned. However, the curve gradually levels off and does not fully reach the desired value, showing the presence of steady state error, which is a common limitation of a P controller. Okay, this graph shows the closed loop response of the system using a PI controller. The output increases over time and continues to rise until it reaches the desired value, showing that the integral action successfully eliminates steady state error. Compared to the P controller, the response is lower at the beginning but more accurate in the long run. So the curve indicates stable behavior, although the sharp increase near the end suggests that improper tuning may cause excessive accumulation of error, highlighting the importance of carefully selecting the PI gains. Okay, so I will explain about the system and description and assumption. So the system is a DC motor speed control system where the input is the armature voltage and the output is the angular speed of the motor. So feedback is obtained using a tachometer to measure the motor speed. So the system is assumed to operate under linear condition with viscous friction taken into account. So it is also assumed that the load torque varies within known and acceptable limit, allowing the control design to focus on normal operating conditions. So for the mathematical modeling, in this stage, the electrical and mechanical dynamic of DC motor are modeled analytically. So differential equations are derived based on standard motor principle to describe the relation between voltage, current, torque, and speed. So these equations are then combined to obtain the transfer function of the system, which serve as the foundation for controller design and performance analysis.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zafitri bin Saidin. My mission number is 231360054. So today I will explain about the slide for slide 9, 10, 11 and 12 for assignment for subject control system technology. So as you can see, first slide is slide 9, which is closed loop block diagram. You see this is the diagram, and I will explain a little bit about the slide. So this slide shows that the closed loop block diagram using a P controller, the error between the reference speed and actual speed is processed by controller to generate the motor input. It improves response speed but still leaves steady state error. And then we move to the next slide, which is closed loop block diagram PI controller. So as you can see, this is the for the this is the block diagram. I will explain a bit about the block diagram. So as you can see, this slide shows the system using a PI controller. The proportional action improves the response, while the integral action eliminates steady state error. This makes the system more accurate and stable, even when load is disturbance occur. And then I will move to the next slide, which is slide 11. So for the slide 11, it is controller design approach. So for the controller design approach, this slide explain the controller design that the P controller improves response speed but cannot remove steady state error. The PI controller is more suitable because it improves stability and reduces error. The PID controller offers the best performance but require more complex. And then lastly, I will explain about the slide 12, so which is for the identification of uncertainty. So as you can see, this slide is about explain the main source of uncertainty in the system. First, load torque variation, where the motor load changes unpredictably and affect the speed. And then secondly, parameter variations such as changes in inertia and friction due to temperature or wear. And then for the third one is measurement noise, where the sensor may produce small error in the feedback signal. And lastly is this uncertainties can reduce performance and must be considered in controller design. So that's all from me. Thank you so much.
Hello, Assalamualaikum. My name is Samir Syamil Salihim bin Zaidin. My matrix number is 231363007. So today I will explain about simulation and performance analysis. Simulation results show that the open loop system has a slow response and a large steady state error. The P controller improves the speed response but cannot eliminate the error. But with the Pi controllers, zero steady state error is achieved and a significant improvement in speed regulation is also observed under load disturbance condition. Next, for stability and uncertainty analysis. The stability of the system was evaluated through closed loop analysis. All closed loop poles are located in left half of the S-plane, confirming system stability. The system also remains stable even when controller parameters vary, demonstrating robustness. So next, managing uncertainties in speed control system. In practical environments, speed control systems are affected by various uncertainties. First, load-induced speed disturbance can cause speed fluctuation. This issue is addressed using feedback control, which continuously regulates the speed and correct any deviation. Second, uncertain mechanical losses such as friction and inertia variation may introduce steady state error. To overcome this. Integral action is included in the controller. This helps minimize steady state speed error and improve long-term speed accuracy. Third, noise in speed measurement can degrade performance. This problem is managed by properly tuning the controller gains to reduce noise amplification. And lastly, system parameter variation may affect stability. Robust controller tuning ensures the system remains stable and reduce dependence on precise system modeling. Okay, next for the conclusion. For the conclusion, a feedback speed control system was successfully designed and analyzed. A Pi controller was selected because it provides a good balance between simplicity and robustness. The system operates stably under uncertain load conditions, making it suitable for real industrial application. That's all from us. Thank you.